here we are, lesson 5.3, biogeochemical cycles. So now we're into the last part where we're talking about those nutrients and how they travel through the ecosystems. And it's all a cycle. Remember that matter is being recycled, so it's never leaving the ecosystem. It's just being reabsorbed in a different way. And so the elements or molecules of the nutrients are traveling through the atmosphere, so the air, the hydrosphere, through the water, through the lithosphere, which is the mantle, the upper mantle, and the crust, so they could be in the ground, and the biosphere, so in our living things in dynamic equilibrium. Remember that dynamic equilibrium is where we are at a steady state, but that steady state can go up a little bit and down a little bit. So it's moving, things are going back and forth, but we're staying at a steady state. And nutrients are stored in what's called a reservoir. So that's a place where there's a lot of nutrients of one kind, or a pool to another reservoir for a varying amount of time called the residence time. So there are a bunch of different reservoirs of carbon, any living thing. So for example, you, right there, a cow, grass, sedimentary rocks, which are not alive. My dog Honey, who's barking, she's a reservoir for carbon. And the atmosphere are all reservoirs for carbon. When a reservoir is releasing more materials than it accepts, it's called a source. So it's a source for that nutrient. So it's giving away that nutrient. When a reservoir accepts more materials than it releases, it's called a sink. So you can think of nutrients as flowing there and staying there. So you can think of it as a tap water, or as a tap. So a sink or a source is the faucet letting the nutrients go, and the reservoir is accepting it. It's called the sink. And flux is the rate at which materials move between reservoirs. So if there's a large flux, then it would be going quickly from source to sink and staying there for a long residence time. And the sink is slowly releasing them at a small flux. So the first is the water cycle or the hydrocycle. I'm sure you've learned about the water cycle at some point in your life, but the water cycle is super important for all other cycles because water, like we talked about in one of the first chapters, is the main medium or way that the biochemical reactions happen, and it's in every environmental system. So it carries nutrients, sediments, and pollutions. It's how nutrients move around our bodies. It's how they move around plants. It's how they move a lot of times in the air, in the water, obviously. And it returns atmospheric pollutants to the surface through rain or snow. So anything that gets into the air comes back to the earth through water through precipitation. So the hydrologic cycle summarizes how water flows as a liquid, a solid, and gas through our environment. So the oceans are the main reservoir of water, 97%. But the reason why sometimes we have water shortages is because we can't process that water because it's salt water. Only about 3% of the Earth's water is fresh water, and 2/3 of that 3%. So 2% of all the water, so only 1%, start that over. All the fresh water in the earth is only 3% of the earth's water, and 2/3 of that water is frozen in glaciers, ice caps, and snowfields. So only 1% of the earth's water is available to us as fresh water. Evaporation is when water is stored as a liquid and it's returned to a gaseous form. This is increased by warmth, wind, and a high degree of exposure. I'm sure that makes sense to you. So as temperature increases, there's going to be more evaporation. As wind increases, there will be more evaporation. And the more that water is exposed to the atmosphere, then there will be more evaporation. So evaporation takes water, fresh water or salt water, and returns it to the atmosphere. Transpiration is when plants breathe, basically. So it's the release of water vapor by plants through their leaves. So plants also perform cellular respiration. So when they are releasing that water from cellular respiration, that's called transpiration. And transpiration and evaporation both leave any substances dissolved in the water behind. So the water that's coming out is fresh water. So any toxins that are in soil that plants take up through their roots, they do not lose when they evaporate water through transpiration. Instead, it's stored in the plants and then can be eaten by the other things in the ecosystem. So that's how water gets to the atmosphere from evaporation and transpiration. It's returned to the Earth's surface as precipitation through rain or snow. And then when it's returned to the Earth's surface, it can be taken up by plants or used by animals, but most of it flows as runoff into surface waters. So this is, again, where a watershed is coming from. So some precipitation in surface water soaks down through soil and rock. So it soaks all the way down. It becomes groundwater. Groundwater is all the water that's underneath in the soil and the rock. And there are these huge places of underwater or underground water storage called aquifers. It's not like a tank underwater, it's just regions of rock and soil that are able to store a lot of water. And so groundwater, when the ground absorbs the water from the runoff, it recharges the aquifers and restores them. So this is the aquifer down here, and the groundwater restores that. So now we've have precipitation landing on the earth and on the water in the ocean. So the precipitation that hits the ground, a lot of it is taken up as groundwater, and then a lot of groundwater is released to the ocean or stored in the aquifer. So the upper limit of groundwater is called the water table, and this is where we see surface water. So this is where we have lakes or springs or things like that. So when it's in the water table, so this higher level of the ground, that's when groundwater is up towards the top and we can see it. The rest of it is stored in the aquifer below. And I'm sure that you could guess this, but our impacts on the water cycle are huge. So human activity basically affects every aspect of the water cycle. So when we dam a river to create a lake or to divert flow, we're slowing the movement of water and increasing evaporation from reservoirs, because now it's a higher level of exposure. So that was one of the things that increased evaporation. Removing vegetation through deforestation increases runoff. So water isn't being absorbed by the plants and now has no place to go. So it's running off into surface water, and it decreases infiltration and transpiration. So obviously we're not having as much transpiration if we're cutting down the plants. Transpiration being the evaporation of water from plants. Withdrawal of groundwater, so we are tapping into the groundwater to drink or to use as fresh water, and that lowers the water table. So the water table is up here. This is where right here, this is where the groundwater meets the surface, and if we get rid of that groundwater, that level goes down. And then air pollution can change the chemical nature of precipitation, which we'll talk about a lot later. But when we put pollutants into the air, that comes back down to the Earth's surface through the water cycle. So that's the water cycle. Next, we'll get into the carbon cycle. So carbon is a nutrient. It is found in every single organic molecule. Remember that we have carbohydrates, fats, proteins, and nucleic acids. It's also in nucleic acids, and it makes up all living organisms, so it's super important for us. It's what makes up all biomass. All biomass has carbon in it. So the carbon cycle describes the routes that carbon takes through the environment, because remember, all nutrients are cycled. So here's an image of the carbon cycle. So plants use carbon dioxide from the atmosphere and that's how we get carbon dioxide and have it stored as carbon compounds, those proteins, carbohydrates, lipids, and nucleic acids. And that's the primary productivity, that right there. Then carbon dioxide is returned so this is the gross primary productivity. That's what this arrow is showing. It's taking the carbon out of the atmosphere and putting it into plants. And that is the only way that we are able to take carbon dioxide out of the atmosphere. It also goes into the ocean, ocean atmospheric exchange. We'll talk about that in a minute. But basically, the producers, so the plants, algae, and cyanobacteria, they take carbon dioxide out of the air and make glucose from it. So that's what this arrow is showing. We're taking the GPP, the gross primary productivity. Then autotrophs, consumers, and decomposers. Every living thing takes organic molecules and releases some of the carbon as carbon dioxide. And so that's what respiration is. So all living things are reducing carbon dioxide as respiration. So the forests are, the consumers are. Over here, the autotrophs here and the consumers here are releasing carbon dioxide through respiration. And then the remainder that we're not breathing out as carbon dioxide is what is making up every part of you. So every part of your body, structural, is made of carbon dioxide, or carbon. It has carbon in it. So when aquatic organisms die, their remains settle in the sediments in the ocean or in the bottom of the fresh water, and over a long time, the pressure will convert their soft tissues into oil, fossil fuels, and skeletons may become sedimentary rock like limestone. So they may become sedimentary rock, like we said down here, or it may become fossil fuels. And then sedimentary rock is the largest reservoir in the carbon cycle. So it's the place where the most carbon is being stored, and it's released during uplift as the plate tectonics are moving it through erosion, just over time as it's broken down, volcanic eruptions, or the burning of fossil fuels. So if you look here, the fossil fuels are stored in the sedimentary rock. So down here, this is the largest source of fossil fuels. So this is being released more than it's being put into, making it a source. It's a reservoir. The oceans are the second largest reservoir of carbon dioxide because gases can be dissolved in the ocean, and carbon dioxide is one of them that's dissolved in the ocean. And a lot of the living things that live in the ocean incorporate this carbon dioxide once it's in the water. It's called carbonate or bicarbonate, and then that makes the shells of many marine organisms. So this is a very complicated cycle. It's much more complicated than the water cycle. So there's several different sources. So take a look at each of these arrows and see if you can understand where they're coming from. But we are now creating a change in the carbon cycle. By now, I mean the last few hundred years. We're shifting carbon from the lithosphere to the atmosphere, the lithosphere being the sedimentary rock where it's stored. And now we're creating the atmosphere into a carbon dioxide reservoir because of the combustion of fossil fuels, and the decrease of surface vegetation. So we're cutting down plants who would be taking the carbon dioxide out of the air, and we're increasing the burning of fossil fuels, which is putting carbon dioxide into the air. And a lot of the excess carbon dioxide is being absorbed by the ocean. So the ocean is becoming more acidic, which is what's leading to things like coral bleaching. And about 2.3 to 2.6 billion metric tons of released fossil fuel CO2 is unaccounted for, meaning it's just in the atmosphere. So not very good. All right, that's the carbon cycle. Then we have the nitrogen cycle. The nitrogen cycle involves now these specialized bacteria that we need to survive. So nitrogen is an essential ingredient in DNA, RNA, and proteins. If you remember, the nitrogenous bases, adenine, guanine, thymine, and cytosine in uracil, made up of nitrogen. Nitrogen gas, N2, is the most prevalent gas in the atmosphere, but we can't do anything with it. It's chemically inert, back to your chemistry days, meaning that it's non-reactive. There's no way to get it to react with anything. And so it's not leaving the atmosphere without assistance. So you breathe in nitrogen and breathe it back out exactly the same way it came in. Your body can't process it. But under the right conditions, nitrogen can become biologically active, meaning it'll change forms and then be able to be used inside living things. And it will enter the biosphere, aka be processed in your body, and the lithosphere in the ground in a process called the nitrogen cycle. So here's the nitrogen cycle. Again, pretty crazy. So to become biologically available, meaning it changes from N2 to a form that can be processed and stored and used in your body, it's called nitrogen fixation. So it combines nitrogen with hydrogen to form ammonia. And then ammonia and ammonium are two different forms of the same product. And then that can be taken up by plants. So nitrogen is combined with hydrogen, and now it's ammonia, which will be taken up by plants. Intense energy of lightning strikes can also fix bacteria or fix nitrogen. So we see that nitrogen fixation is happening here, where it says assimilation. And also fixation by lightning can bring it back into the organic matter in the ground. Okay, so the way that this happens is that we have what's called nitrogen fixing bacteria. So they're bacteria that convert nitrogen gas into ammonia, into that NH3. And the bacteria live on the plant roots. They form nodules there, and they absorb sugars from the roots in exchange for nitrogen fixation. So this is a symbiotic relationship, a commensalism. They're both now a mutualism. They're both gaining something. Plants are gaining the ammonia that they need. We can't live without it. And the bacteria are taking sugars from the plants as they make them. And so legumes such as soybeans are ones that this happens very often. And so this is the little nodules on the root, and there's tons of nitrogen fixing bacteria there. So they're taking the N2 and turning it into ammonia, which can be used. Other bacteria perform a process called nitrification. So we had nitrogen fixation, which turns it into ammonia. And then we have nitrification, which turns that ammonia into nitrate ions, nitrate or nitrite, which plants then can directly use. So a lot of times we'll also add these to the soil through the use of fertilizer. So in order to remember that nitrogen is a limiting factor for marine ecosystems, and also terrestrial ecosystems needed as well. So we'll give them this nitrate and nitrite through fertilizer, so that way it doesn't have to happen all naturally through nitrification. And consumers, we get nitrogen by eating plants or other animals, so we cannot do this process. And then decomposers will take the nitrogen from dead organisms and release it. Denitrifying bacteria will convert these nitrates and nitrites back into nitrogen gas and release it back into the atmosphere and complete